Hey everybody, today we are going to be talking about the Squeeze Theorem. It's a very interesting theorem, and I want to give a huge shout out to Parth Panchal. I'm not sure if I'm pronouncing your name properly, but he's the one that originally suggested this. And yeah, so I'm going to be doing a video on it. So this theorem has a few other names. It's like the police theorem or whatever, but Squeeze Theorem is the most common name. And essentially it says that we have three functions here, f, g, and h, and they're defined on an interval here where they kind of meet up at x equals a, right? And we notice that h of x is greater than or equal to f of x for all x in the interval, and g of x is less than or equal to f of x for all x in the interval. So g is a lower bound, h is an upper bound. But they seem to meet up at x equals a, and that's interesting because we can conclude that the limit as x approaches a of h of x, if that's equal to the limit as x approaches a of g of x, then the limit as x approaches a of f of x should also be equal to that same number. Now I'm not going to do a proof of this because that requires some weird things and stuff, but I'm just going to kind of show you the intuition for why this is true. So we have here, we have these functions and we're trying to basically find the limit. So you can see that's kind of why it's called a squeeze theorem, because we're squeezing our function f between g and h, and that way we can find what our limit is. So, for example, let's say, well actually let's just kind of write down our statement. So let's say let f, g, and h be functions defined, defined on an interval I. Interval. So yeah, we're going to let these functions be defined on this interval. And now what we need to do is kind of say, well, okay, if these limits, if the limit of g and h are equal, then, that's at a, then the limit of f should be equal. So suppose, now I'm going to say that the limits of g and h are equal, so I'm going to just speed up the video just to make that a little quicker. Okay, so I decided to call this some capital L, right? So if these two things are true, then that tells us that the limit as x approaches a of f of x equals L. And that should be pretty easy to see, right? If the limits of these two guys, they're going to squeeze through, and f is going to just be there. So that's pretty much the theorem. You probably could add a little more. Wikipedia, its definition talks a little bit about limit points. So I'll just kind of write that down. So we got limit points. And that's more of a topological concept, but I can kind of talk about that. It says that A is a limit point of this interval. Okay, so actually I do want to say there are functions defined on the interval, let me put I, and then they don't have to include the A. I forget, actually, I think the backslash goes this way. Yeah, I think so. So A, they could like cross over a little bit at A, or, not really, but like, that's kind of just how the definition is. But yeah, so it talks about limit points on Wikipedia. So a limit point is another name for it is an accumulation point. So accumulation point, and it's basically exactly what you think about. It's a place where the set kind of just accumulates. So so let's say if we have a great example of a limit point is if we have an interval here. Let's say it's a how do I want to do this? I think it's going to be open. So we have 0 here and we have 1. and then let's say we have x sub n, some recursive statement, or not recursive, but I forget what these are called. So it's going to be 1 minus 1 over n. And so yeah, if n is equal to 1, we have 1 minus 1 over 1. So 1 minus 1 is 0. So actually this does have to be like that. So now we have a half open interval, right? So actually a funny name for this is actually also called a clopen interval, because it's closed and open. So I don't know, that's funny. But so yeah, so we have this interval. So 1 minus 1 over 1 is 0. 1 minus a half. So yeah, this first point, 1 minus 1 over 1, then 1 minus a half, then 1 minus a third is about 2/3, 1 minus a quarter is about 3/4, and you can see that this guy is going to keep going all the way over here. Now, is it ever going to actually reach 1? No, because 1 minus 1 over a million is not exactly 1. So we can kind of show this. So let's first assume that 1 minus 1 over n equals 1, right? Let's assume that at some point this is true and we're trying to find the n value that works for this. So let's actually, I can rationalize the denominator a bit, so it's going to be, or not rationalize, but like combine these. So this turns into n minus 1 over n is equal to 1. So if n minus 1, I can multiply both sides by n, and we just get n minus 1 equals n. And this is never true, because if we subtract n on both sides, we get negative 1 equals 0. And that is not true. So this never actually reaches 1, but it gets really close. It just goes very, very, very close. And so 1 is actually an accumulation point for on this interval for this function. So that's kind of an accumulation point that you can kind of think of everything getting like super close together, and just kind of accumulating there. So that's basically it for the squeeze theorem. I could have proven it, but I might do that in the future if I feel like it. But yeah, so I hope you guys enjoyed. Thank you for watching, and I'll see you in the next video. Bye guys.